Now let's consider one more way of looking at practically realizable filters. So again, let's consider this ideal low-pass filter, which has this magnitude transfer function that is this perfect rectangle. And then depending on the time delay, we see that we have different slope angles in the phase. Now, if we were to take this, right, go from the frequency domain and pass this into the time domain via the inverse Fourier transform, what we have already seen is that this is non-causal, right? So this ideal low-pass filter is actually non-causal, and we know that because if we look at time equals 0, we see that for all three of these time delays, the system is responding prior to time equals 0. So this is a non-causal system, which means that it cannot be physically realized. However, there are a couple things we noticed, which is that the increase in time delay moved this large pulse further in time, meaning that in the time before 0, we had a smaller ripple. So if we were to try to realize this filter, so if we were to try to get an approximation of this ideal filter, we had two ideas. The first idea is increase your time delay. So make your time delay very large. Maybe it approaches infinity. The second, so this is the first idea. The second idea was let's apply a step function to each one of these. Now, if we apply a step function, we can see in MATLAB that if we were to plot this, this means that there would be no system response before time equals 0. This would turn it into a causal system. That doesn't mean the ripples go away though, right? The ripples just immediately stop right at 0, and then before 0, they are equal to 0. So what effect would that have on the filter? So if we were then to take this, right, so these are our new time domain, what if we were then to pass this into the frequency domain? How would this affect this? What kind of distortion would we get? What kind of distortion would we get in both the magnitude and the phase? So we're going to look at this by using the fast Fourier transform. And it turns out that the phase is going to be a little messy, but we can clearly see the effect of this step function on the magnitude response. So for the ideal filter, if we have a time delay of 1 millisecond, we can see in the magnitude response, this when we go back into the magnitude, if we take the magnitude of our cutoff transfer function and then pass it back into the frequency domain, we see that it has some ripples. It no longer is following this flat response. We can see that there's some very clear distortion that's going to occur in the magnitude. And that distortion, it happens across the entire frequency band, right? So these low frequencies, we see that the amplitude response is less than 1, so we're actually attenuating it a bit. However, at our mid frequencies, here, our time delay, by making it into a physically realizable filter, is actually adding some amplitude response. And then, as we approach our former bandwidth, right, so that we previously had this perfect cutoff right at 1000 hertz, and we can see that if we try to realize this practical filter where we apply a step function and a time delay, we see that there is going to be an attenuation that starts to happen around this 700 hertz, and then is already quite attenuated by the time we reach our former cutoff frequency. Now what's happening is we can see that this is right at 0.707. So we've already gotten quite a bit of attenuation at this time. Now, if we look at other time delays, we can see that increasing the time delay has a couple of effects. It changes the size of the ripples, right? So these purple ripples are quite a bit smaller, so you have less amplitude distortion, but you still get this kind of precipitous cutoff where all of a sudden before our previous 1000 hertz, maybe here at 900, 950, we're even for a large time delay, we're seeing a precipitous cutoff they all appear to cross over right around here at 0.707. And this shows us that we can use the fast Fourier transform to see what a realizable filter would look like. So all these filters with ripples are filters that you can actually realize. So whenever you try to make this type of ideal filter, if you were to pass it back, if you were to try to realize it by applying the step function and pass it back into the frequency domain, you'll see that the effect of applying the increased time delay and the step function is still going to result in some ripples, some non-ideal components, and you're going to be adding some distortion simply by trying to realize an ideal filter. So no filter that we actually build is going to be ideal. They're all going to have some type of distortion. As for this part in the phase response, I believe this is probably just an artifact of the sampling on the FFT and is a bit noisy, so we'll just disregard that for now.